Hey everyone! In this 5-part video series, we're going to be exploring the strong nuclear force from a gauge-theoretic perspective. That is to say, we're going to be deriving the foundations of quantum chromodynamics from SU3 color symmetry. Alright, let's do it. This topic is a sequel to my video on electromagnetism as a gauge theory, in which we saw that the U1 symmetry group at the core of electromagnetism gives rise to the photon field and the Lagrangian of quantum electrodynamics, and then ultimately to all of the electromagnetic phenomena. All of that blossoms out of this magical principle of local U1 symmetry. Well, today we're going to do exactly the same thing, but we're going to switch out the U1 for SU3, and we'll get into what that means. But in spirit, it's exactly the same as what we did for electromagnetism. We're going to start with the principle of local SU3 symmetry. That's going to blossom into the gluon fields and the Lagrangian of quantum chromodynamics. And then we're going to develop this understanding that the strong nuclear force is actually just the manifestation of local SU3 symmetry. It's a beautiful, incredible thing. I mean, it's like, wow. Okay, and before we get into it, I know the question is going to come up. What are these symmetry principles anyway? U1, SU3, where do they come from? Well, the truth is no one knows. And so you may as well think of these symmetry principles as like magic beans. You know, the thing about a magic bean is it works whether or not you know where it came from. If you plant it, it'll burst forth magnificently into a beautiful magical beanstalk. And that happens here too. So U1 sprouts into electromagnetism, and local SU3 sprouts into the strong force. And one of the main themes of this video is that the way in which those beans grow is identical for both electromagnetism and the strong force, even though the symmetry groups are different, and even though, experimentally, electromagnetism and the strong force have very different characteristics. At the end of the day, both of them can be very deeply understood from a gauge-theoretic perspective. Alright, well, to set expectations, let me just say that quantum chromodynamics is a massive subject. It's the kind of thing that you could study for years and years, and decades, and maybe someday in the future, with medicinal breakthroughs, you could study QCD for centuries and centuries. But we don't have all that time in this video series. We only have a few hours. Oh, by the way, I went ahead and broke up the video into 5 parts. Based on some of your comments, I figured that it's probably a good idea to break up these big videos into more, self-contained parts that are more appropriate length. So when I say this video, what I really mean is parts 1 through 5. And, we can leave it open-ended, so maybe someday there might be a part 6, but cross that bridge when we get there, okay? In parts 1 through 5, we're going to cover all the things on the left side of your screen. So we'll get into the concept of a quark color triplet field psi. We're going to talk about group theory and the unitary groups and the special unitary groups and their Lie algebras. And of course, we'll emphasize SU3 as well as SU3. And we'll talk about generators and the Gell-Mann matrices. We'll talk about the structure constants. We'll introduce a gauge covariant derivative for QCD. We'll talk about gluon fields and how those live in SU3. We'll talk about the gluon's field strength tensor, which is a really interesting thing. And then once we've assembled all the ingredients of QCD, we can look at the gauge transformation rules and how to hop from one gauge to another. And at that point, we'll be ready to put together the whole Lagrangian of quantum chromodynamics. And once we investigate that Lagrangian, we'll see that there's naturally 3 and 4 gluon interactions, which is what makes the gluon fields kind of sticky. And that's the thing that gives rise to gluon flux tubes and color confinement and all that good stuff. And then at the end of the video, we'll wrap things up with a comparison of the abelian gauge theory of electromagnetism with the non-abelian gauge theory of QCD, and we'll also generalize so that you can start thinking about these grand unified theories and a more holistic picture of what gauge theory can be. Alright, but that said, there are some things we're not going to cover just because it'll take us too long to cover them. These things are more advanced. And so we're not going to get into like the quark masses and why they are what they are, or chiral symmetry breaking, or hadronization, or lattice QCD, Wilson loops, or normalization, the running of the strong coupling constant, asymptotic freedom, or the details of color confinement, and all that kind of stuff. There's a whole world out there of quantum chromodynamics that we're not going to be getting into in this 5-part video series. Although maybe we can come back to some of those someday if I ever end up doing a part 6 or a part 7. Well, in any case, if you want to learn the stuff on the right side of the screen, first you have to learn the stuff on the left side of the screen, so that's what our focus is going to be on. And for what it's worth, the things on the left side of your screen, that's like the main philosophical tree trunk that everything else branches out from, you know? So that's like the backstory of where each of the ingredients of QCD comes from, and how it all ties back to local SU3 symmetry. Okay, now to orient ourselves, let's take a look at the standard model gauge group. So we have color SU3, we have the SU2 pertaining to the left-handed weak isospin doublets, and we also have the hypercharge U1. The subscripts C, L, and Y stand for color, left-handed, and hypercharge, respectively. In this video, of course, we're going to be focused on the color SU3 of the strong force, and the SU2L cross U1Y, that is the gauge group of the electroweak sector, which we're not going to worry about today. And by the way, in our universe, the gauge group of the electroweak sector is highly modified by the presence of the Higgs field, which is sort of like a superconducting condensate that exists everywhere throughout spacetime. The Higgs field effectively breaks down SU2L cross U1Y into the U1 of electromagnetism that we actually observe. And in the process, it basically turns off the remaining 3 degrees of freedom that pertain to the weak nuclear force. Anyway, we're not going to focus on that today. If you're curious, I do have a video called Superconductivity and the Higgs Field, where we go into that in more detail. But never mind that for now. Today, let's focus only on the color SU3 of the strong force. Well, before we dive into things, let me just say that this video series is going to be very, very mathematical. It'll be very similar to the electromagnetism video, but a little bit more intense. And that's just because SU3 is more complicated than U1. So in the interest of time, anything that we covered in the electromagnetism video we'll take as a prerequisite for today's video. So for example, when we talk about like the Dirac Lagrangian, I'm not going to rehash where that comes from, but I will put a timestamp of where we talked about it in the electromagnetism video. And I'll also cite equation numbers from the following 2 books. First up, we have Introduction to Elementary Particles by David Griffiths, and that's the same book that we referenced in the electromagnetism video. And then today, I'm also going to pull in Gauge Theories of the Strong, Weak, and Electromagnetic Interactions by Chris Quigg. And that's one of the books that we referenced in Superconductivity and the Higgs field. So even though this video is going to be very mathematical, I hope that it also contains all the references that you need in order to learn more about the mathematical details if there's something that you want to brush up on. Okay, but before we get into the mathematically intense stuff, let's go ahead and ease into the subject matter by taking a moment just to casually meditate on the nature of things. So, you may have heard that once you've read the dictionary, every other book is just a remix. Well, likewise, everything is just a remix of the periodic table. And it's a remarkable fact that all the stuff around you, and including you, is just an arrangement of all the same atoms that are everywhere throughout the universe. That's a pretty neat thing to ponder. But then the question becomes, what are atoms? Well, if you want to understand atoms, start with hydrogen. It's the simplest atom, just a proton and an electron, and it gives us a great way of putting together a mental picture of the kind of thing that an atom is. Basically, what you have is a very massive but very dense proton, and then an electron which is much less massive, and so its position is much less certain. The electron wants to come in, but if the electron gets too close, if its position becomes too localized, then its momentum uncertainty becomes very big, and then at that point you don't know how fast it's going, and so it can never actually collapse into the proton. It just becomes this poofy, fuzzy quantum situation. And one way to think about the ground state of the hydrogen atom is as a balance between the attractive Coulomb force and the uncertainty principle that keeps the electron spread out. Now, if you give the atom a kick, the electron can be excited into a higher energy state. And what's interesting is that there's only a discrete set of different ways to do that. And the reason for that can be readily understood. The electron's wave function has to be continuous and smooth, and what that implies is that there's going to be a discrete set of energy eigenstates, which are roughly speaking sort of like vibrational modes. These are often called orbitals. Now, if you try to apply the same analysis to heavier elements, you find that it actually gets much more complicated, especially because of the way the electrons interact with each other. But having seen hydrogen, you can still get the basis of a mental picture for how atoms work in general. There's a very small, dense nucleus, and around that there exist these very cloudy, fuzzy electrons with various orbitals. And the reason I bring this up is to emphasize the point that the behavior of atoms in everyday life is almost entirely due to the interactions of the electrons with electrons from neighboring atoms. So when you think about chemistry and you think about things like ionic bonds and covalent bonds and all that sort of thing, van der Waals forces and what have you, those have a lot to do with the way that the electrons are behaving. But the nucleus of the atom, the protons, the neutrons, those pretty much stay put at the center of the atom. And the nucleus of one atom doesn't really interact too much with the nucleus of another atom. So whatever is going on with that very tiny, very dense nucleus is almost like a hidden world within a world. It's not something that we really access very often. And when we do, the results are quite dramatic. Whenever there's a nuclear thing, it has a kind of surreal intensity to it. Because you're dealing with forces that don't normally manifest. So evolution hasn't equipped us with an intuitive understanding of the nucleus of an atom. And therefore, when we zoom in and take a look at the nucleus of an atom, we should not expect it to be normal and understandable and to make sense. No, we should expect it to be weird. And it's not weird that it's weird. It'd be weird if it wasn't weird. So keep that in mind, because the more we learn about the nucleus of an atom and quarks and gluons, it is all very, very strange. And a lot of it kind of comes off as an affront to the intuition, but just remember that's what we would expect, because we're exploring something that we don't normally have access to. All right, so the first thing you should know about the nucleus of an atom is that it is very, very small. So here, I've used a very sophisticated high-resolution rendering technique to draw a picture of an atom represented by a blue circle and a nucleus represented by an orange circle. And you might think, wow, that nucleus is pretty small. But this diagram is actually not to scale. In reality, the nucleus is actually much, much smaller relative to an atom. Now, if you want to put a number on that and say, how much smaller is the nucleus than the atom? Well, an atom is about a few angstroms wide. Of course, that kind of depends on how you define the size of the atom, because it's kind of a fuzzy thing. But let's say it's some fraction of a nanometer. Well, the nucleus is only a few femtometers wide, which is 10 to the minus 15 meters. So that's actually about 100,000 times smaller than the atom, linearly. And by volume, if you cube that, the nucleus is about a quadrillion times smaller than an atom, which is crazy. No one even uses the word quadrillion. No one knows what that is. It's so high, it's even higher than the US national debt. Whoa. Okay, enough of that. But if you want to put a picture on it, imagine a grain of rice inside a stadium. That's more or less about the order of magnitude that we're talking about here. So that's pretty crazy. You often hear that an atom is 99.999 lots of nines % empty space. But think about what that implies for the density of the nucleus. If all of the mass of the matter that you're made out of, or almost all of it, is contained in the nucleus, because electrons are super lightweight, to a very good approximation, the mass of an atom is basically just the mass of the nucleus. But if all of that is inside a grain of rice in the stadium that is the atom, then if you zoom in on that nucleus, what you find is something absolutely insanely dense. Like we're talking about 12 trillion times denser than tungsten. And tungsten is already dense enough to change your whole perspective on life. So imagine 12 trillion times that. It's just insane. And that's just part of the weirdness that is the atomic nucleus. That tiny little speck has almost the intensity of a neutron star when you think about it. It's crazy. Okay, so what is the nucleus of an atom? Well, you learn in school that the nucleus of an atom is comprised of protons and neutrons. And that's true, but protons and neutrons are not elementary particles. Each of them are comprised of 3 quarks, bound by the strong nuclear force, which is mediated by gluons. And that's the level of detail that people don't normally go into when they're talking about the nucleus of an atom. I mean, normally you just talk about protons and neutrons, But today we're zooming all the way in, so we gotta deal with quarks and gluons. Now a proton is 2 up quarks and 1 down quark, and a neutron is 1 up quark and 2 down quarks. An up quark has an electric charge of 2/3 the elementary charge, and a down quark has a charge of -1/3 the elementary charge. So when you put them all together, you find that a proton with its 2 ups and 1 down has a net charge of +1, and the neutron with its 1 up and 2 downs has a net charge of 0. And so that's why the proton is positive and the neutron is neutral. But here's where things get super, super weird. Quarks have a surreal property known as color, which has absolutely no place in the world of conventional sanity. Now, I know that sounds like outrageous hyperbole. What do I mean, no place in the world of conventional sanity? But when you think about it, it's like, okay, back in the day when you were born, you were a little baby, and then you grew up and you talked to people and you learned about the world and they told you stories and maybe you had a religion or a political view or whatever. And you kind of got a sense of like a worldview and how the world works and what's going on here and what was history about and what kind of animals lived here and what are the plants, and you learn about all these different things in life. And quark color is just no part of that whatsoever. It's a complete stranger to the intuition, and it's something that we have to learn brand new. We have to confront it using the tools of mathematics in order to try to get a grasp of what's going on here. And it's an astonishing fact that the math actually can help us understand this concept that is otherwise so utterly foreign to the human mind. One of the first questions that comes up when you hear about color is, how do we know that color is a thing? What experimental data compels us to come to that conclusion? And we'll get to that in just a second. But first, let's take a moment to just kind of review the concept of color and what it is and how it manifests in nature. So first of all, color has nothing to do with color. Color is just a metaphor. As we'll talk about throughout the rest of this video series, color is really just a label that we put on the index of the Quark color triplet field, and we'll get into that. But basically, color is a helpful metaphor that helps us keep track of the math and gives us a nice, comfortable way of thinking about these ideas. So if you look at the diagrams shown here for the proton and neutron, you see that you've got 3 quarks, and you've got a red one, a green one, and a blue one. Now there's a sense in which those colors are balanced. Just like if you think about a pixel on a TV screen, when you have red, green, and blue all lit up by the same amount, from a distance that pixel is going to appear gray or white. And so from a distance, there's no net color to a proton or a neutron. From a distance, they look gray, so to speak. And that's not a coincidence, but that's actually an example of the concept of color confinement. You know, the study of the strong force, it's called quantum chromodynamics because chromo, meaning color, is the central aspect from which the strong force originates. And it's a remarkable mystery that any bound state of quarks, like for example the proton and the neutron, are all color neutral. In other words, the colors are balanced, red, green, and blue, and they always will be. You know, if you imagine a hydrogen atom, you can take off the electron, you can ionize it, and you end up with a proton over here and an electron over there. So you can separate electric charges, but you can't separate color. You can't take the blue quark off of a proton and end up with a blue quark over here and a red and green pair of quarks over there. No, it doesn't work. The colors always have to be confined into these color-neutral states where everything balances out. So if you use the analogy of a pixel, every particle is gray when viewed from a distance. There's that equal balancing of red, green, and blue. Now this is quite a bizarre situation, and it's something that we should be able to account for theoretically. So one of the main tests of any theory of quantum chromodynamics is that it has to provide a natural explanation for color confinement. And actually it does, as we'll see, though admittedly the math is very complicated. But the gist of it is that local SU3 symmetry gives rise to gluon-gluon interactions, then you get gluon flux tubes, and then you get a binding force that increases with quark separation. So the more you try to pull quarks apart, the more they want to stick together, and that leads to color confinement. And we'll get to that later. But for now, for starters, we're going to go ahead and take color confinement as just an empirical law. It's a mystery that we'll keep in mind as we're developing the model of quantum chromodynamics. Okay, so I have a thought experiment for you that's going to help us understand why color is a thing. And I like to call this thought experiment the dizzy protons and neutrons. Okay, so as we've seen, protons and neutrons are both bound states of 3 quarks. Proton is up, up, down, and neutron is up, down, down. Now both the proton and the neutron have a spin of 1/2. And quarks also have spin 1/2. And so the spin 1/2 of a proton and a neutron you can think of as being the result of two of those quarks having their spins aligned, and one quark being the odd one out, being oppositely aligned to the other two. Now in reality, it's a little more complicated than that because it's a quantum thing, and so technically it's a superposition of all the different ways that you can have quarks that are two of them one way and the other one the other way. But in any case, the spins of the quarks combine such that the net spin is 1/2. So here's the thought experiment. Is it possible to have the same trio of quarks, up, up, down, and up, down, down, but in states where all the spins are aligned? Well, if so, then those would be like spin 3/2 versions of the proton and neutron. So it's the same quark content, but it's in like a spin-excited state. See, that's what I mean by dizzy protons and neutrons. All the spins are aligned. They're really spinny. Well, as it turns out, yes, these do exist. But they're extremely unstable. The half-life is only 6 × 10⁻24 seconds. But they can exist. The fabric of nature can vibe in that way. And that tells us something about the structure of quarks and gluons and the physics of the situation. Even knowing that this little dizzy proton and neutron can exist for the tiniest little blip of time gives us a hint about the secret behavior of quarks. But there's a problem. If we call them dizzy protons and neutrons, that sounds too whimsical. People are going to think we're a bunch of goofy goobers. That's no good. You know what would be more formal? Instead of dizzy, let's just use the letter D. And instead of protons and neutrons, we'll call them baryons, where a baryon is just the generic kind of 3-quark situation. So protons and neutrons are both baryons. And these dizzy protons and neutrons, if we call them D baryons, doesn't that sound way more technical? I think so. But you know what? Actually, better yet, instead of D, let's use the Greek letter delta. Delta baryons. Now that sounds like a technical word. And in fact, that's actually what they're called. So you thought I was just being goofy and whimsical calling them dizzy protons and neutrons, but actually secretly this whole time that's a mnemonic device for the delta baryons. Okay, so we got the delta plus, and that's like a dizzy proton. It's also up, up, down, but in a spin 3/2 state. And then we have the delta zero, which is like the spin 3/2 version of a neutron. By the way, these are often called delta resonances because they're so short-lived, they're so unstable that in a way you can think about it as sort of like an excited state of a proton or a neutron. Okay, but now there seems to be a problem here. Because when you think about it, it's like, hold on. Don't the delta baryons violate the spin statistics theorem? Because all of the spins are aligned. And so you've got this situation where for the delta plus, you have these two up quarks that are the same quark, spins aligned the same direction, so that should be two quarks in the same quantum state. And it's the same for delta zero. In that case, you have two down quarks in the same quantum state. And that should be impossible because quarks are fermions. And so they should obey the Pauli exclusion principle. So what's happening here? It's crazy. The reason why is that the spin statistics theorem requires multi-fermion wave functions to be antisymmetric under particle exchange. What that means is that if you have a multi-particle wave function, let's call it psi AB for particles A and B, then if you switch the particles, so you switch A for B, and A and B are fermions, then the wave function should pick up a minus sign. That's what antisymmetric means. So psi AB equals negative psi BA. And that implies the Pauli exclusion principle, because if you have two of the same particles and you try to switch them, you find that psi AA equals negative psi AA. So the states are the same, and yet they're different by a minus sign, and the only thing that's the same and also different by a minus sign is 0. So there's 0 probability of having two fermions in the same quantum state. And therefore, if we look at the wave function of a delta plus baryon, what we find is that psi of up, up, down should equal negative psi of up, up, down, where you switch the ups, so it's the same, but it's the opposite, so it should be 0. There should be 0 probability of having delta baryons, okay? They don't make any sense. Now you might be thinking, okay, well, maybe this is just a violation of the spin statistics theorem. The problem is there is no such thing as a violation of the spin statistics theorem. The spin statistics theorem is one of the things at the absolute foundation of physics, and there's no getting around it. And you know what? It gets even worse. Because collider experiments have shown that you also have delta plus plus, which is 3 up quarks in the same spin state, and you have delta minus, which is 3 down quarks in the same spin state. So those also exist, and those seem to have 3 fermions in the same quantum state, which is just preposterous. I mean, this is absolutely absurd. So what is going on here? Well, the conclusion that you have to come to is that the situation is simply not possible. And yet, it's how it is. And if it's how it is, then that is how it be. And if that's how it be, then not only is it possible, but it's inevitable. And if it's inevitable, then it can't be not possible, because it has to be possible in order to be. And so we have to think of what can be such that delta baryons can be. Like, what do we have to add to our understanding of the physical world in order to not run into a paradox when we think about the existence of delta baryons? Well, what it comes down to is quarks need to have access to a surreal internal degree of freedom, which has no macroscopic analog. We don't see it in other particles. It's not part of what we observe on a daily basis. It has no place in conventional sanity, and yet it is there in the quarks. It's the degree of freedom that allows delta baryons to exist without violating the spin statistics theorem. Now, I should point out that there's all kinds of other reasons why we would think that quark color exists, not least because you can build all of quantum chromodynamics based on SU3 color symmetry. So the model works very well, and color is a core part of it. But I just bring up the delta baryons as a really stark example of the fact that quarks have this weird behavior that does require them to have some kind of unusual, surreal attribute. And so that's what color is. All right, hey, you know what? While we're on this topic, the question comes up. If we can have 3 quark particles, like protons, neutrons, delta baryons, well, why not 2? Why can't we have a pair of quarks? Well, at first glance, you would think maybe you can't have 2 quark particles because of color confinement. As we talked about earlier, the colors have to balance out. You need an equal amount of red, green, and blue. So for example, if you had a proton with a red up quark and a green up quark and a blue down quark, then you've got a perfect balance of each color. But if you just had a couple of up quarks, say 1 red, 1 green, well then you don't have enough blue. So from a distance, that particle would not have a neutral color. It would have color. And that breaks the rule of color confinement, so that can't exist, right? But don't forget about antimatter. Every particle has an antiparticle. And remember, color isn't really color. Color is a metaphor. And so an antiparticle can have a kind of anti-color. So for example, if you have a green quark, well, you could also have an anti-green antiquark. When we're talking in terms of color, that doesn't really make a whole lot of sense. You're like, anti-green. What does that even mean, you know? But it'll make sense later when we dive into the math. And in the meantime, I mean, it kind of makes sense, right? Like anti-green. You know, it's green, but the opposite. Okay. It makes sense insofar as you can imagine that green balances out anti-green, so that this pair of quark-antiquark actually is colorless. And yeah, these do exist. Although, of course, they're also very unstable. These 2 quark states, they're called mesons. It's a quark-antiquark pair. And the most basic and common example are the pi mesons. So for example, pi plus is an up quark and an anti-down quark. Pi naught is a superposition of an up quark with an anti-up quark and a down quark with an anti-down quark. And pi minus is a down quark with an anti-up quark. Now the pi mesons are the primary culprits for the residual strong force, which binds the protons and neutrons together in the nucleus. Because when you think about it, it's like, okay, why doesn't the nucleus of an atom explode? Because all of the protons have positive electric charge, so they want to repel. But the strong force holds the protons and neutrons together. However, the strong force that holds the quarks together within a proton or within a neutron, that's really like the pure strong force. That's like the direct color SU3 gluons quark situation. But then when you zoom out and you think about the fact that protons and neutrons are all color neutral from a distance, then the question comes up of like, what sticks those together? And the answer is that there's a residual strong force, which is mediated by things like pi mesons, And those effects aren't as strong as like the real actual strong force that binds quarks within protons and neutrons. And yet it is still strong enough to overcome the electrostatic repulsion of the protons in the nucleus of an atom, up to a certain size. If a nucleus gets too big, then it becomes unstable. Okay, so we've been talking about up quarks and down quarks, but those aren't the only kind of quarks, you see, because there are actually 3 generations of matter. For example, the electron has 2 heavier unstable cousins, the muon and the tau. And as far as anyone can tell, the muon and the tau are basically the same thing as an electron, but they just have a lot more mass, and no one really knows why. And likewise, along with the electron, we have the neutrino, the electron neutrino, but those also have 2 cousins. You have the muon neutrino, and you have the tau neutrino. So if you just think about the electrons and the neutrinos, you can see that you have 3 generations of matter. But the same thing applies to the quarks. Again, you have 3 generations. So the up quark has 2 heavier cousins, which are known as the charm quark and the top quark. And then the down quark has 2 heavier cousins, known as the strange quark and the bottom quark. And nobody knows why. This 3-generation thing is a super deep mystery. It's something that even in this day and age, in the year 2025, no one knows why this is the case, but we know that it is the case. Now, the reason I bring this up is that this gives us additional context on the behavior of quarks and gluons, because we've seen now how you can think about the delta baryons and the pi mesons as examples of different particles that you can make out of quarks, and even though they're unstable, they tell us something about the behavior of quarks. And likewise, in particle accelerator experiments, things can reach such a high energy that you can produce these particles that involve 2nd and 3rd generation quarks. And you can study those as well and examine their properties and their masses and their decay modes. And that gives us a tremendous amount of context about the nature of quarks and gluons. So when you factor in the 2nd and 3rd generation quarks, you see that there's a whole particle zoo of baryons and mesons. Oh, by the way, so baryons are 3 quark particles, and mesons are 2 quark particles. But in general, if you're talking about n quark particles, you can call those hadrons. So a hadron is a particle that's made out of quarks. One of the first questions that comes up when you learn about quarks is, well, wait a minute, if color confinement means that we can never see a single quark on its own, because a quark has color, and there's no way for something that has color to not have color, then how can we believe in quarks, right? Like, aren't quarks this thing we shouldn't believe in if we can't see them? But then if you think about it, it's like, okay, but if we can observe the hadron spectrum, that is the set of the various bound states you can make out of quarks that are bound together by gluons, and if you study the properties of those hadrons, then that gives you like a fingerprint of quantum chromodynamics. So in other words, even though QCD is based on this idea about quarks, and you can never see a single quark on its own, nonetheless, the model still has a lot of credibility because hadrons can be observed, and their behavior matches exactly what we would expect if we had quarks that were bound together by gluons. So if we want to understand what quarks are up to, we should take a moment to examine what are the various kinds of hadrons. Okay, so here I'm showing a list of a bunch of different baryons. Now, we're not going to go through this in detail, okay? I mean, in the interest of time, I'm just showing you the table here so that you can get a sense of some of the particles that we can make out of 3 quarks. So you have the proton and the neutron that we know and love. You also have the delta baryons. And you have all kinds of other things too, where if you look at the quark content, you can see that a lot of these particles involve 2nd and 3rd generation quarks. And as you can see, the properties of these particles have been very precisely measured in terms of their mass and their lifetime and the principal decay modes. And so that gives us a tremendous amount of information about what quarks and gluons are up to and how they can be. Now you'll notice that these are all super unstable. And people often joke about, why do particle physicists get so excited when they discover something that only exists for 10 to the minus whatever seconds, right? I mean, you can't build something out of matter that's so unstable. But the point is to think about the fabric of reality itself as a kind of instrument and then ask, what are the notes that it can play? And then you take note of those notes. And then that teaches you something about what's going on in nature. So yeah, our matter is made out of protons and neutrons, and those are the stable baryons. But to understand their constituent quarks and gluons and what's really going on there, the unstable baryons give you a whole lot of puzzle pieces to work with, and so this information has really been super important for the development of quantum chromodynamics. Now, one thing I'll say before we move on from this table is if you look at the neutron row, the second row there, you can see that technically its half-life is 880 seconds, which is only like 15 minutes. And it is actually true that if you had a neutron floating through space, then pretty quickly it's going to decay into a proton, an electron, and an electron antineutrino. So it's a fun fact that neutrons are technically unstable. But if you look at how long the half-life is, 880 seconds, that's way, way, way more than like 10 to the minus 10 or 10 to the minus 20 seconds. And a big part of why the neutron is so stable is that if you look at the mass gap between a neutron and a proton, there's hardly any mass gap there at all, right? I mean, you got 0.93828 versus 0.93957. It's like, yeah, the neutron is technically slightly more massive than the proton, so there's some driving impetus for the neutron to relax into a lower energy state by decaying into a proton, electron, and electron antineutrino. But there's really not much of an energy benefit, and so there's not a whole lot of pressure, so to speak, for the neutron to decay into a proton. And also, the way in which the neutron decays happens via the weak nuclear force, which is super weak, and so it's super unlikely to happen. So you have a combination of not a whole lot of driving force for the decay, as well as a super unlikely decay mode, and that's why, on the timescale of particle physics, where things happen in femtoseconds and nanoseconds, the neutron basically lives almost an eternity on that timescale, but it can eventually decay into a proton. Now, in your atoms, neutrons generally do not decay into protons, because in the context of an atomic nucleus, that tiny little difference between the mass of a neutron and a proton often is smaller than the energy cost of adding another proton to the nucleus. When you think about the whole energetic situation in the nucleus, you have to ask yourself, is that tiny little bit of mass energy released when a neutron becomes a proton worth being able to accommodate an extra proton in the atom? And usually for stable matter, the answer is no. But there are some isotopes where actually the neutron does kind of want to become a proton, and in those atoms you can actually have a neutron becoming a proton. And when that happens, that's something called beta-minus decay. And they call it beta-minus decay because the atom emits an electron which is negatively charged, but that leaves behind an extra positive charge in the nucleus of the atom. So when beta-minus decay occurs, the element actually becomes a new element, which is one higher on the periodic table. Oh, and then one last thing, on the half-life of the proton, what I've put there is at least 3 times 10 to the 41 seconds. Now, that's not to suggest that the proton is unstable. According to the standard model, the proton should be totally stable, it should never decay, and its half-life should be forever and ever. But there are some speculative reasons to believe that perhaps the proton might be unstable over extraordinarily long timescales. The reason being, you have these grand unified theories in which the gauge group of the standard model is a fragmented, broken down version of something more elegant like SU5 or SO10, and in such models, you have extra Higgs fields that break down that symmetry at a super high energy scale. So you know how the Higgs field breaks down the electroweak sector into electromagnetism and the weak nuclear force, which it basically turns off? Well, the idea is that in those grand unified models, those extra Higgs fields are going to break down that unified symmetry group, but you'll have like these super duper weak, ultra suppressed interactions, sort of like a version of the weak nuclear force that's way weaker, but those interactions could in principle cause a proton to decay, though that would be super unlikely. Now, people have looked for proton decay, and so far they haven't found anything, and so the experimental lower limit is something on the order of 10 to the 41 seconds, which is very many times the lifetime of the universe. Now, of course, those experiments didn't wait that long to get to that result, but no, instead how they do it is they look at very, very many protons for some period of time, And then they say, okay, well, if none of those protons decayed, then we know the half-life has to statistically be at least this super long time period. Now let's look at a table of mesons. So as we talked about, we have the good old pi mesons, pi plus minus, as well as pi naught, but you can also make other mesons if you include the quarks from the second and third generations. Now I'm really not going to linger on this at all because today we're not trying to dive into the details of all the different possible hadrons, but I just bring this up to give you a sense of the context of the subject matter that we're talking about today. And if you want, you can pause the video and look up any of these mesons and you can learn more about them. Now the mesons I'm showing here, these are called the pseudo-scalar mesons because they're spin zero. So remember, a meson is a quark-antiquark pair. Quarks have a spin 1/2, and so in all of the pseudoscalar mesons, the spins of the two quarks are oppositely aligned such that the net spin is 0. Now a scalar particle like the Higgs boson is going to have a spin of 0, and so that's why these are called pseudoscalar mesons. They're not fundamental scalars, they're this combination of two quarks with oppositely aligned spins, but because the spins cancel out, from a spin perspective, they're sort of like scalar particles. So you might be thinking, well, hey, is it possible to have a quark-antiquark pair where the spins line up in the same direction, and so you have a spin 1 particle? And yeah, totally, for sure. So these are called the vector mesons because they have a spin of 1, and when you have a quark-antiquark pair where the spins are aligned, 1/2 plus 1/2 equals 1, and so, these are known as the vector mesons. Well, anyway, I just wanted to show you some of the hadrons so you can get a sense of the kind of ways that quarks can interact with each other to form these bound states, even if they're super unstable. But for the rest of this video series, I want to meditate on the wave function of just a single up quark. The reason being, everything we're going to be talking about from the perspective of local SU3 symmetry and the gluon fields and all of that, you can derive just by thinking about the wave function of a single up quark. And in fact, we can make our lives easier if we want to, and we can think about a single up quark in a momentum eigenstate where the momentum is precisely known, and even in a color eigenstate if we want, where the color is precisely known. Because if we imagine the simplest possible quark wave function, that'll work just fine for being the thing that we imagine when we think about the way that a local SU3 transformation is going to mess things up, and when we think about the way that our gauge field is going to come in and clean up that mess. And the way I like to think about this is, if you knit a sweater out of thread that's made of cotton, then the sweater is made out of cotton. What I mean by that is, when we think about the way that an SU3 transformation messes up a quark triplet field, which we'll get into in a moment, we may as well imagine a very simple quark triplet field, because there's no need to overcomplicate it. But with our equations, we'll call that triplet field psi, and we're not going to bake any constraints into our equations about it having to be a momentum eigenstate or about it having to be a particular color. So we have this simple mental image, but the equations are actually going to be totally generic. Oh, and just a reminder, so a momentum eigenstate is a state where the particle's momentum is precisely known, but then as a result, because of the uncertainty principle, we know nothing about the particle's position. Now in reality, this is kind of an idealization because you never precisely know the momentum, and you never totally don't know the position, but, position is too casual. But when you think about it from the perspective of Fourier analysis, and you imagine a more generic wave function that can be expressed as a superposition of these plane wave momentum eigenstates, then you see that if what we're talking about regarding how QCD blossoms from local SU3 symmetry applies to a momentum eigenstate in a way that carries through when you superimpose a bunch of momentum eigenstates into a more generic wave function, then we may as well think only about the simple eigenstate when thinking about how the gluon fields are going to arise naturally from local SU3 symmetry. Okay, so I've been using some terminology like quark triplet field and local SU3 symmetry that we haven't precisely defined yet. So I want to take a moment just to go into some technical detail. So first of all, the wave function of a spin 1/2 particle is going to be a Dirac bispinor field, which has 4 complex components, as we've seen in previous videos. If you want to see a derivation of that, you can check out my video deriving the Dirac equation. But then also, as we've seen, if you want to focus purely on a matter solution or an antimatter solution on its own, then you can treat the wave function as a two-component spinor-valued wave function to a pretty good approximation. But anyway, I have some good news for you. As we think about the way in which quantum chromodynamics blossoms from local SU3 symmetry, we're not going to emphasize the spinor nature of our wave function at all. Instead, we're going to focus our attention on the color degree of freedom. And so this is why, for example, in this animation of the green eigenstate, what I'm showing at each point is simply one complex number, because even though technically, mathematically, the full wave function is going to be this Dirac bispinor field, we may as well think about this simply as a phase factor which is evolving in space and time, and we're going to carry through the spinor structure in our equations. But we don't have to bring it to the front of our imagination. We can send it back to the subconscious, making sure it's there in the equations, but not making it the primary object of our attention. And then if we suppress those spinor details to the back of our mind, that gives us the imaginative space that we need to bring in this new degree of freedom, of color. So now let's see how exactly we can do that. Well, imagine we have a green quark in a momentum eigenstate. We can write its wave function as the product of a Dirac bispinor times an exponential, which for the matter solution is going to be e to the negative I et minus p dot x. And all that is a plane wave solution. It's just a momentum eigenstate for a matter particle, where the function inside the exponential governs the space-time evolution of that plane wave. And then the u sub s term is 4 complex numbers corresponding to the spin state of the particle. So now if we want to imagine, in addition to green quarks, we could also have red quarks or blue quarks. Well, all we have to do is copy and paste the same thing, but we'll make one red and we'll make the other one blue. And now there you have it. There's a red quark, a green quark, and a blue quark. Okay, but what even is red, green, and blue? You know, like, that's not math, that's a color. What are we doing here? Well, think of it like this. What if we merged these three fields together into a single field, which can be thought of as a kind of field that has this 3-layer color degree of freedom situation? So at each point in spacetime, rather than having a single Dirac bispinor, now we have 3. And so at each point, we have the red wave function, we have the green wave function, and we have the blue wave function. Now, if we want to make sense of what kinds of laws of physics could possibly govern a field like this, we'll have to come up with a Lagrangian. And the most simple way to do that is simply to say that if we have a free quark, meaning it's not in any kind of potential or anything, it's just floating through the vacuum of space, and we'll start off with a model where the 3 colors are non-interacting with each other. So we haven't turned on quantum chromodynamics yet. We're just going to say that the Lagrangian of the triplet field is simply the sum of the Lagrangian of the red field plus the Lagrangian of the green field plus the Lagrangian of the blue field. And so you see how we've put in no interactions between the different colors. As we've written it here, this Lagrangian describes a model where the red part, the green part, and the blue part of our triplet field are all totally independent of one another. Whatever's going on with one color has no effect on anything that's happening in another color. Now, when we derive the Lagrangian of quantum chromodynamics, it's different, because that Lagrangian is going to have interaction terms such that the colors are all related and dynamically intertwined. But that's something we're going to have to develop based on SU3 symmetry. For now, we're just thinking of a way of combining this 3 degree of freedom situation into one kind of multifaceted field that we can think of as a color triplet field. Now, the Lagrangian of a free spin 1/2 particle is given by the Dirac Lagrangian. So all we have to do is write out the Dirac Lagrangian for our red, green, and blue wave functions. So in each case, in natural units, we're going to have psi bar I gamma mu partial mu minus m psi. Now, if you look at a Lagrangian like this, it looks pretty redundant, right? And I mean, that's kind of what we would expect. Problem is, if you work with this for a while and you write this out, your hand will get tired because you're going to keep writing out the same thing over and over again. And once you've written this Lagrangian a few times, well, I mean, actually, if you've only written it once, then you've already written it a few times. You're going to get tired of having to write this out over and over again. And sooner or later, you're going to realize, hey, wait a minute. What if we write the Lagrangian like so? We'll use a capital psi bar I gamma mu partial mu minus m capital psi, where this capital psi is just the three lowercase psi's in a container. And, spiritually, that's kind of what we should have in mind when we think about superimposing the different colors into a field. Well, what better way to do that than simply have a column where the components of the column are each color of the wave function? And so that's kind of the intuitive visual geometric picture. But then we can also think about it algebraically. If we write out capital psi as a column of the lowercase colored psi's, then the Dirac adjoint of capital psi is going to be a row containing the Dirac adjoint of each of these colored wave functions. And then by inspection, if you simply substitute that into our Lagrangian equation, you can see that indeed this does equal the triply redundant expression that we wrote out previously. So there's a way of looking at what we've just done here as nothing more than a convenient move to be able to write our Lagrangian more elegantly. And that way our hand doesn't get tired when we're doing this kind of physics. And again, as we've written it here, at this point, there are no interactions between the different colored components of our triplet field. We haven't baked those into our model yet. At this moment, all our triplet field is a way of thinking about multiple different colors of a wave function at the same time. It's basically like having three independent layers of a Dirac bispinor field that are sort of associated together, like they sort of live in this same complex triplet structure, but the different components within the triplet don't yet affect one another. Oh, and also I just want to emphasize that, remember, behind the scenes, each one of these colored lowercase psi's is actually a Dirac bispinor field with 4 complex components. But we can put that to the back of our mind, and we can focus primarily on the color triplet structure of our wave function. Now, as we go into more detail in the later parts of this video series, we'll see exactly how that works out algebraically. So it's okay if for now you just have kind of a visual mental image, but we don't have to precisely articulate all of the mathematical details just yet. Think of this video as like we're just kind of easing into the subject matter. It's just kind of like a preview of the math to get us thinking about what comes next. All right, so you know what? There's another way to think about this color triplet field, which is it's not just a way of merging together 3 different Dirac bispinor fields, but we can think of it as a mathematical entity in its own right. And in fact, when you think about the color triplet field psi as its own entity, you realize then that color is nothing more than which component of the triplet field we're talking about. So when you talk about a red quark, all that means is a quark that lives in the top component of psi. You talk about a green quark, that's a quark that lives in the middle component of psi. A blue quark is a quark that lives on the bottom component of psi. A quark that's in a superposition of these different colors, it's going to have some, different numbers for the different components of psi. So you see now that color is just a metaphor. It's just a way of making the equations more visual and easier to imagine. But it's not really like color. It's just a kind of mental trick to make the math more familiar. And now once you see that, you think like, oh, great, and well, now let's be really sophisticated, and we don't have to think in terms of color anymore, we can just think of it purely algebraically. But then you think about it a little longer, and you're like, actually, you know what, this color thing is pretty nice. It makes the equations easier to deal with, so that's why we're going to keep talking in terms of red, green, and blue. All right, so now while we're here, on the topic of a quark color triplet field, the question comes up, what would happen if we required that our Lagrangian would remain totally unchanged under any transformation where the triplet field psi becomes psi prime, which is defined as U times psi, where U is a field of SU3 matrices that varies arbitrarily in space and time? And we'll get into what exactly that means, but basically what it means is that suppose we demand that we should be able to mess around with what we mean by color at different points in space and time, and we want that to have no effect on our laws of physics. Well, the Lagrangian we've written here doesn't naturally have local SU3 symmetry. But if we insist that it has to, and then if we modify it in whatever way is necessary in order to give it that symmetry, then our Lagrangian is necessarily going to evolve into the Lagrangian of quantum chromodynamics. And that is the central theme of this video series, is seeing how if we impose local SU3 symmetry onto our Lagrangian, then we have no choice but to unleash the strong nuclear force, which is just an incredibly mind-blowing thing to think about. All right, so I want to focus in on some of the technical details here. So this is the Dirac Lagrangian, and it describes a quark color triplet field that is floating freely throughout space-time, and that doesn't yet have interactions between its various color components. We haven't added those in yet. So this Lagrangian would encode the laws of physics for our triplet field, which is what Lagrangians do, but on its own, this doesn't yet give us quantum chromodynamics. I mean, mathematically, this is just equivalent to 3 totally non-interacting spin 1/2 particles. But then we have this notion of local SU3 symmetry, and we can say that our laws of physics have local SU3 symmetry if the Lagrangian remains unchanged by the transformation of psi becoming U psi, where U is a field of SU3 matrices, and all that means is they are 3x3 complex-valued matrices, such that the transpose conjugate of the matrix times itself equals the identity, and the determinant of the matrix equals 1. Now in the next video, part 2, we're going to do a deep dive into group theory, and we're going to talk about the unitary matrices and the special unitary matrices, and that'll teach us what's the deal with the U dagger U equals I and the determinant of U equals 1. So that's what the next video is going to be all about. And then once we have a good understanding of SU3, we'll really be able to imagine the kind of thing that our matrix field is. Because you can imagine an arbitrary SU3 matrix at different points in spacetime. And by the way, that's what makes the transformation local. So instead, if the transformation were global, then that would be the same SU3 matrix multiplied everywhere, basically a rotation of our coordinate system in color space. But a local transformation is a much more interesting thing, because what that means is that we're redefining what we mean by color different amounts at different points in space and time. And when we do this, when we convert psi into psi prime, we often call that a gauge transformation. Although typically when you talk about a gauge transformation, that also refers to the corresponding transformation in our gauge field. So psi becomes psi prime, and g mu becomes g mu prime. And that we're going to talk about in part 3 when we derive the gauge field. Then in part 4, we're going to derive the field strength tensor. Then in part 5, we're going to derive the whole Lagrangian of quantum chromodynamics. So that's what we're going to do. And everything we're going to do is all in service of this remarkable fact that simply by demanding that our Lagrangian have local SU3 color symmetry, we can derive quantum chromodynamics. Oh, also, I want to say thank you to everyone who's been supporting the channel on Patreon. It really means a lot. Like, seriously, your support is what makes this possible. I want to give a special shout out to Jack Serino, who has been supporting the channel at a whopping $100 a month for a while now. It's absolutely incredible. I don't even know what to say. I am beyond grateful. Thank you so much. You're an absolute legend. And also a shout out to everyone else who signed up on Tier 2. Your generous support really goes a long way, so thank you so much. All right, I'll see you next time.